Earlier in this talk, I suggested that there may be a biosynthetic connection between D-glucuronic acid and L-rhamnose. On the basis of modern knowledge of the biosynthesis of D-glucuronic acid, on the biosynthesis of L-rhamnose, on the biosynthesis of D-galacturonic acid, and on the biosynthesis of polysaccharides, I'd like to show that there could well be a biosynthetic connection between D-glucuronic acid, D-galacturonic acid, and L-rhamnose. All chemists know about ATP, adenosine triphosphate, but you can also get nucleotide diphosphates. And one of these nucleotides, uridine diphosphate, can link up with glucose to give uridine diphosphate glucose, which can be written as UDPG. Then the presence of an enzyme galactowaldenase, you could get an equilibrium mixture of uridine diphosphate glucose and uridine diphosphate galactose. There are enzymes in mung beans which can cause the oxidation of these to give you uridine diphosphate glucuronic acid and uridine diphosphate galacturonic acid. Another nucleotide is thymidine diphosphate glucose. In the presence of a number of different enzymes, thymidine diphosphate glucose can be converted into thymidine diphosphate L-rhamnose. So starting with glucose, you could get nucleotides which contain D-glucuronic acid, D-galacturonic acid, and L-rhamnose. There are also enzymes known as the glycoside transferases, which can transfer the sugar part of a nucleoside to react with another monosaccharide. So if you were to take uridine diphosphate glucose and fructose in solution and add the correct transferase, you would get the glucose removed from the nucleoside to react with fructose to give sucrose. And sucrose has been made in this way. But these glycoside transferases can not only transfer monosaccharides to another monosaccharide, it can transfer it to another oligosaccharide, and this can happen over and over again, and this is the way in which polysaccharides are biosynthesized. So starting with glucose, we can get nucleosides which contain D-glucuronic acid, D-galacturonic acid, and L-rhamnose. So therefore, in the presence of the correct transferases, you would expect to get polysaccharides which contain D-glucuronic acid and D-galacturonic acid if there is a biochemical connection between these two. And this is what you do find. Then if there's a biochemical connection between D-glucuronic acid and L-rhamnose, you'd expect to get polysaccharides which contain D-glucuronic acid and L-rhamnose, and that's what you find. Now, if you think that there could be a biosynthetic connection between D-galacturonic acid and L-rhamnose, you'd expect to find polysaccharides which contain D-galacturonic acid and rhamnose, and you do. What about polysaccharides which contain all three? Glucuronic, I don't know of any, but I think they could well be found. But even if one of these is found, or one is known and I don't know about it, it will still be necessary to find an experimental method to demonstrate that the biosyntheses of D-glucuronic acid, D-galacturonic acid, and L-rhamnose are in fact connected. In 1963, I was back working in the chemistry department at the University of Cape Town, and I thought I'd reinvestigate a gum from Acacia cynophila and try out the method which I developed in Edinburgh. Because the Acacia cynophila gum was much more acidic than gum arabic, I found that the diborane reaction only gave 50% reduction. However, in the original paper, Stephen and Smith stated that if you have problems, instead of starting with the acetate, start with the propionate. So I made the propionate and found that reduction gave me 90% reduction. I also found that in the acetylysis, I found better results if I first acetylated the reduced polymer. And then everything went smoothly. I found the exact same disaccharide which I'd found in Edinburgh, and that was the result I expected to find, and I decided not to publish the work. However, in 1973, Bengt Lindberg showed that one of the bacterial polysaccharides contained rhamnose linked to the 4 position of glucuronic acid. Lindberg's method was completely different from the method which I had used. Lindberg first fully methylated the bacterial polysaccharide. Now take a look at the formula. It can be seen that the O prime is linked not only to the 4 position of the glucuronic acid, but it's also in the beta position to the methyl ester group. And when esters like that are treated with very strong alkali, you get a beta elimination reaction and the OR prime leaves. Lindberg used sodium methoxide for 15 minutes at room temperature. He first analyzed the polymer before reacting with the sodium methoxide, and he also analyzed the product after reacting with sodium methoxide. By comparing the 2 different results, he could see which residue had been lost. Using this alkaline method, elimination method, Lindberg and his associates and also some other groups showed that rhamnose was linked to the 4 position of glucuronic acid in several of these different bacterial polysaccharides. And those results stimulated Fugedi in Hungary to try and synthesize the disaccharide where L-rhamnose was linked to the 4 position of deglucuronic acid. Fugedi published the synthesis in 1987. He first synthesized the disaccharide where rhamnose was linked to the 4 position of glucose, and all the hydroxyl groups were protected with the exception of the hydroxymethyl group, the CH2OH group of the glucose. He oxidized the CH2OH to carboxyl and removed the protecting groups, and that gave him his final product. In this day and age, many synthetic organic chemists avoid the use of protecting groups, but I think that protecting groups are still of some value in certain areas of organic chemistry.